Hello, I'm Rachel. Today I'm going to be talking about quantifying the relationship between archaeological sites and hydrologic features, a case study. This study has been the focus of my final part of my master's degree here at the University of Arizona. In archaeology, proximity to water sources has been utilized as a main variable in archaeological site predictive modeling. Archaeological site predictive modeling has become popular due to focusing research efforts and management decisions. Though there has been limited research quantifying the correlation between archaeological site locations and water sources. The Sand Hollow area located in the Virgin River Basin in southern Utah has had multiple archaeological investigations completed by various researchers and companies due to modern construction projects such as the Sand Hollow Reservoir, State Route 7, and the Quail Creek Reservoir. In Shifting Sands by Talbot and Richens in 2009, the main assumption about archaeological sites within the area is that there is association with riverine and drainage systems. For the study, there were two research questions asked. Is there a correlation between archaeological site locations and hydrologic features? And if there is a correlation, does the relationship change based on the time period of the archaeological site in the Sand Hollow area? To complete this analysis, two different data sets were used. The first data set was a digital elevation model, or DEM. The DEM was downloaded prior to June 2000 to remove any impacts from modern construction of the Sand Hollow Reservoir on the derived hydrologic features done through the analysis of the DEM. The second data set was archaeological site locations, which were digitized from site information data from maps within the publicly available report, Shifting Sands. This was due to sensitivity restrictions of more recent investigations. The digitized data from Shifting Sands was defined into three different time period categories of archaic, Anasazi, and late prehistoric, with the archaic being the oldest and late prehistoric being the most recent occupation within the Sand Hollow area. For the methods of this study, 5 steps were taken to look at and quantify the relationship between archaeological site locations and hydrologic features within the Sand Hollow area. The first step was to download the digital elevation model and digitize archaeological site data, as previously discussed. The second step was to complete hydrologic feature analysis. The third step was to prepare data for the chi-square test. The fourth step was to complete the chi-square test statistical analysis. And the fifth and final step of the study was to analyze the output of both the GIS analysis and the chi-square test to look at the relationship between archaeological site locations and hydrologic features within the Sand Hollow area. To look at the hydrologic feature analysis in more detail, the first step was to analyze the digital elevation model for sinks, which are usually errors within the DEM, and to fill them. This is shown here in the workflow that was completed in Model Builder, with each step done to identify the sinks and then to fill them. The next step was to take this DEM and calculate the flow direction and accumulation using the hydrologic toolset in the Esri ArcGIS Pro software. This is shown here in the steps taken in the workflow in Model Builder. The last step of the hydrologic feature analysis was to take the output from the flow direction and accumulation and to complete the stream network analysis. Two different stream network analyses were used of the stream and Strahler. These usually show two different aspects of a stream network. Though for this study, the output of the stream and Strahler were compared for the higher magnitude streams, and there was no difference found between the two different data sets. Thus, either output could be utilized for the next step of completing an analysis for this study. After completing the hydrologic feature analysis, the output was then taken and the hydrologic features were buffered at 100, 200, 300, 400, 500, and greater than 500 meters to start preparing the data for the chi-square test. These buffer zones were then taken and the summarized incident tool was utilized to calculate the site numbers found within each buffer zone. The summarized incident tool is usually used for crime analysis, but worked really well in this application because of its ability to identify the number of sites within each zone found at a specific distance from the hydrologic feature. This output was then taken into Excel to calculate the chi-square test. and the output from the calculations was then analyzed. This is the preparation workflow as shown in Model Builder for the chi-squared test. The 4 outputs shown on the right side were then taken into Excel to calculate the chi-squared test. To provide some framework on how chi-squared test analysis was utilized within the study, the first thing was to identify the null hypothesis. The null hypothesis is utilized as a way to look at whether or not a sample or data is occurring randomly within a landscape, specifically for this study. For the null hypothesis for this study, the question was whether or not archaeological sites are not related to hydrologic features, and the null hypothesis is utilized to identify whether they are related or are not related. To calculate the chi-squared statistics, a formula is used. The observed frequency is identified using the Simonrise incident tool as previously discussed, and these are the numbers of the actual sites that are located within each buffer range. The expected frequency is a calculated value based on the entirety of the data set. So for example, for the archaeological data set, there would be an overall number of sites. This would be taken and then times by the area that the buffer range represents within the study area. These values are then utilized to populate the formula of observed minus expected squared over expected, which then outputs the chi-squared test statistical number. This test statistic is then taken to compare to a chart, along with one other value, which is called the degrees of freedom. The degrees of freedom for this study was the number of buffer ranges, which is 6, minus 1, which equals the number of degrees of freedom of 5. These two values of the chi-squared test statistic and the value of 5 were then compared, and a p-value was given. The p-value represents the ability to reject or accept the null hypothesis. The smaller the p-value, the more the possibility of rejecting the null hypothesis increases. So now that you have a framework of how some of the analysis was done, here are the results. Overall, archaeological sites showed a visual association with hydrologic features, with having red and orange colors indicating proximity to hydrologic features as shown in this map. The hydrologic features are represented in black. The light yellow indicates sites that are located greater than 500 meters from hydrologic features within the study area. This is the smallest portion of the data set. The chi-squared test does support the visual analysis that was done for the study with the ability to reject the null hypothesis. With the chi-squared test value of 37.96 and compared to a table indicates a 0.5% significance level, which is very low and allows us to, as I mentioned, reject the null hypothesis. This can also be looked at by looking at the observed frequency versus the expected frequency. As shown in the table to the right, the observed frequency numbers are higher as you get closer to hydrologic features, especially compared to the expected frequency, which has a more generalized distribution across the landscape. The archaic sites showed a very similar outline to the archaeological sites within the study area. The red and orange again represents sites that are close to hydrologic features, with only 4 sites located greater than 500 meters away. The chi-squared test, again, does support the ability of that visual association between the hydrologic features and site locations. The null hypothesis is able to be rejected with a chi-squared value of 15.56, which indicates around a 4.5% significance level. Again, the observed frequency versus the expected frequency shows the majority of sites occurring near hydrologic features, with, for example, the buffer range of 0 to 100 meters having more than double the number of sites in the observed versus the expected. The Anasazi does follow along with the same pattern as the archaic and archaeological site data sets. The sites are located near hydrologic features. One interesting thing about the Anasazi is that, as I draw my pointer here, this is the Virgin River, which is the largest surface water feature within the area. The Anasazi were known for doing sedentary farming and would locate areas where there was a year-round water supply, such as the Virgin River. The Anasazi chi-square test also does support the ability to reject the null hypothesis, with having a test value of 26.2 Thi, which indicates a 0.5% significance level. Again, following the same pattern as the archaic and archaeological sites, the observed frequency is higher near hydrologic features than the expected frequencies. The late prehistoric shows a similar visual association with hydrologic features shown in red and orange, and only one site in the light yellow that represents greater than 500 meters. Though, differing from the archaic, Anasazi, and archaeological data sets, the late prehistoric chi-square test did not support this visual association. The null hypothesis could not be rejected, with a test value of 6.33, which indicates a 10 to 90% significance level, which is a lot higher than the former looked at data sets of the archaic, Anasazi, and archaeological sites. As you can see also within the observed frequency and expected frequencies, there's only 1 to 2 number difference between these frequencies that were looked at in this part of the study. So overall, the null hypothesis was able to be rejected for the archaeological site data within the Sand Hollow area. The majority of archaeological sites, about 80%, are within 300 meters of a hydrologic feature. As shown in this map, the buffered area of 300 meters is represented by the hatched area, and the majority sites shown in red and orange are located within that buffered area. The chi-squared test also supports this, with having a significance level of 0.5%, which indicates a strong statistical relationship between archaeological site locations and hydrologic feature locations within a landscape. Not only does the chi-squared test supports the visual association of archaeological sites, but it also supports the assumption that site locations are influenced by proximity to water within the Sand Hollow region. When looking at the time periods, Anasazi and archaic sites have very similar statistically significant correlation to hydrologic features across the landscape. This is similar to the overall archaeological data set, as these 3 data sets were able to reject the null hypothesis that archaeological sites are not related to hydrologic features, and thus represents that archaeological sites within Anasazi and archaic and overall archaeological sites can be said to be associated with hydrologic features within the area. Late prehistoric sites did show a visual association with hydrologic features, but did not show statistically significant relationship via the chi-squared test, and cannot reject that null hypothesis that archaeological sites are not related to hydrologic features. This could partly be due to the size of the data set, as late prehistoric sites was the smallest data set overall out of the 4 data sets that were utilized, but the 3 different time period data sets that were used in this study. In conclusion, statistical and visual analysis do indicate that archaeological sites have a statistically significant relationship to hydrologic features and show a visual association between hydrologic features and archaeological sites. By using derived hydrologic features from a DEM and assumptions concerning site locations, these 2 assumptions could have impacted the results. So for future studies, it is recommended that paleoenvironmental data should be used to model past hydrologic conditions, along with more recent archaeological studies being included within the dataset. To facilitate this, Model Builder was used to create tools for future analyses by researchers. This will also help for researchers to utilize sensitive, restricted data sets in analyzing these patterns. Here are a few key references. I look forward to any questions that you have about my research. Thank you so much for attending my presentation today.